My name is Iulian, I'm a software engineer at Adobe, and today I have the pleasure to present you a project that combines machine learning and Kubernetes and aims to enhance the adoption of AI in the medical domain. The agenda for today's presentation is structured in 4 chapters. Each different, but combined in a common context, produce an interesting story. In the introduction section, we will see the problem we want to solve and what are the different types of solutions we have, with their advantages and disadvantages. Then, moving to the machine learning chapter, we are going to briefly present the dataset, used in our project, how we can build a generative model that will produce images for us, and how to decentralize the model training in order to conserve data privacy. Then we will see how we manage to leverage Kubernetes for training a good generative model in a non-centralized fashion. And lastly, we are going to discuss about the results of this project to confirm its value and especially the idea of combining Federated Learning with Kubernetes. Okay, so to introduce you in the problem, think about the lack of data in the medical field. Data collection can be a costly and a time-consuming process on its own. To mitigate this problem, we want to train a machine learning model capable of identifying underlying patterns and then generating synthetic images to augment and balance the dataset. Also, we aim for removing the pressure from a single training server by decentralizing the augmentation framework. Thus, we will see how we manage to augment a medical imaging dataset and improve the classification accuracy, having in mind that data privacy is a must in the medical domain. Let's start with what we have. As I said earlier, data scarcity is a real problem in the medical field. Also, hospitals do not want to make their datasets public and share them with a training server. Another point would be that there will be a lot of normal data and very few anomaly images that captures different diseases. This will lead to class imbalance. Now moving to the what we want part, besides the fact that we want to mitigate the class imbalance problem, we must also keep the data safe and private without sharing it to anyone. And the question that naturally comes to everyone's mind is, why are you doing this? And the simple answer is that medicine is a huge field worth investing in. Without further ado, let's try to build up our path from what we have to what we want. Let's address the question, how? In order to increase the size of a dataset, we have 3 options. Perform manual data collection, use simple mathematical operations, and train a machine learning model that will generate images for us. Let's take each one individually and see their pros and cons. This will help us identify which option best fits to our case. The first one is manual data collection. This implies that each hospital must have to wait for new patients in order to store their data. The most noticeable pro of this method is the accurate data that we obtain. We get the real images with 100% meaningful information. But there are also some disadvantages. The most important drawback is that the dataset remains unbalanced, and it also takes a lot of time to manually collect real data from patients. Now moving to the mathematical operations, we can apply different image level transformations, like filters, rotations, flips, and so on, in order to capture the same image in different poses. This will lead to the same data distribution, but in the end, we are talking about the same image. This will cause lack of diversity and will damage the patterns of images. Until now, we saw 2 rudimentary data augmentation techniques. But why not to try to train a machine learning model that will generate images for us? We would like to have a model, for now it's only a black box, that will receive some input and generate the desired image. With this approach, the model will be able to learn inner patterns, and this will lead to diversity in the augmented dataset. Also, at inference time, we will be able to generate a lot of images of this type. However, we also need to mention that it's hard to train such a model, and it requires computation resources such as GPUs. To summarize, this project aims to propose a framework for augmenting medical images by distributing computation, and the most important thing, doing this by preserving data privacy. And with this being said, we've just reached the first milestone, where we have talked about what is the problem at hand, what are the main ways to resolve it, and what do we need to keep in mind when trying to resolve it. Of course, we don't want to fix something on one side and mess it up on the other. Now let's move to the second chapter, where we'll talk a little bit about the dataset used in our project, build the generative model, and decentralize the training by introducing the federated learning technique. Each chapter from this milestone is an important building block for gaining a good understanding of what comes after it and for validating the proposed approach. The dataset we will test our project on is a medical imaging dataset, which comprises histological images of colorectal cancer categorized into positive and negative classes. We randomly partition the dataset into training and testing sets on an 80-20 ratio, resulting in over 15,000 training samples and 4,000 testing images. As I said earlier, class imbalance is a real problem in the medical datasets. In our example, there are over 75% negative images and only 25% positive samples. All of these point us in the presented direction. We want to increase the size of a dataset and especially generate images for the class with less samples in order to balance the dataset and enhance the classification performance. Previously, I said that we will use a machine learning model to generate synthetic images in order to increase the dataset, but didn't mention how the architecture looks and how the generative model works. Let's open the box by starting with the basic architecture and then gradually adding some components over it in order to understand the final architecture used in our framework. Let's start with the unconditional generative adversarial network. This architecture consists of two models, a generator and a discriminator. The generator takes random noise as input and tries to produce good images so that the discriminator cannot distinguish between the real and the fake ones. On the other hand, the discriminator takes an image as input and tries to detect if the given image is real or generated. This architecture looks good, but we have a problem. For example, if we want to generate only images from the positive class, we are not able to do that because the model is not aware of the label of each image. It will only generate images either positive or negative. But we can solve this issue by adding constraints to the architecture. By injecting the class information in the framework, we make the models aware of the label of each image. In this way, at inference time, when we generate images, we can easily give to the generator the desired class, in this case positive, and the model will be constrained to generate images only from that class. Now looking at the generator training error, we see that the loss is going to 0 after some training time. At first, it may seem promising, but plotting some generated images during training makes us think that the things are not really going in a good direction. Bad quality images and good generator leads us to think that the discriminator is too powerful compared to the generator. The generator produces bad quality images and yet manages to fool the discriminator. So let's complicate the problem a bit. Let's give the discriminator a harder task. To complicate the things a bit for the discriminator and compete with the generator in a fair game, let's give the discriminator an auxiliary task to also predict the class of the image. The generator is trained in the same way as before, but the generator is now trained in the multitask learning fashion, having to predict both whether an image is real or fake as before, as well as determining its corresponding class. This will lead to a more stable training, and the models will compete against each other in a more balanced way. Now, just by looking at the images, we can easily say that the quality is better and the patterns from the generated images resembles with the ones from the original dataset. So from now on, we will use this architecture to transition from the centralized learning where all data is in one place and the training is done on a single server to a non-centralized solution known as Federated Learning. Thus, we want to decentralize the training by allowing multiple clients, hospitals in our study, to collaboratively train a model without sharing their raw data. Each hospital trains a local model using their private data, and these local models are then aggregated by a central server to construct a global model. This process enables learning across distributed datasets while maintaining data privacy, making it an ideal solution for collaborative medical research. Having this in mind, let's see how federated learning training round looks like. The first step is to initialize the global model on the server. In our presentation, an ACGAN generative model randomly initialized. Then the server sends that randomly initialized model to the connected clients, in our case hospitals. In step 2, each hospital starts with the global model received from the server in the previous step and starts training the generative model locally on their private datasets. This slide best illustrates the decentralization idea by preserving data privacy. Then, after all clients' training procedures are completed, clients return their local models back to the aggregation server. Clients only return the model parameters, not the data itself. That's very important. Thus, after the local models are received from clients, the server aggregates these local models into a global one. By doing these steps, sending the global model to clients, each client training his local model, sending back the model parameters to the server, and aggregating these local models into a global one, we say that we performed a round in the federated learning context. For stabilizing the training and obtaining good performances, several rounds are required. And with this being said, we've just covered the second milestone. This was the most comprehensive chapter from the entire presentation. Now, in order to put the presented framework in a real environment, we will invoke Kubernetes in the game. We have three main options when it comes to choosing the Kubernetes architecture. A hospital can be modeled in one of the following: hospital as a cluster, hospital as a namespace, or hospital as a node. In a production environment, each variant has its own pros and cons, but looking at these options, we clearly see that the simplest solution for validating the training framework is to make the hospital node mapping. Let's see what the cluster setup looks like. We're going to start with a Kubernetes cluster where we have created a namespace in order to isolate our org from other tenants. Next, let's add some nodes with GPU capabilities, starting with the aggregation server node and then continuing with the client's nodes. For this simulation, we choose to have 4 clients, 4 hospitals, which will train their local models and communicate with the central server. Now that we have the environment ready, we can start adding our federated learning application on each node. One thing to note here is that each node has some specific labels and tends to only tolerate custom pods. For ensuring that two pods don't get scheduled on the same node, pod anti-affinity was employed. Good, now that we have the server and clients applications running on each node, we need to establish the communication between clients and server. And for this, we've created a service for each entity. And this is the final architecture of the Kubernetes cluster. The clients can now communicate to the server, and now we are good to go. Let's see it in action with a small demo. In the upper right terminal, I listed all nodes with a custom label. These nodes have a V100 GPU on them. Then in the upper left terminal, I am deploying the server on one of these 5 nodes. The server's pod is up and running and scheduled on a node with GPU capabilities. Now looking at the server's logs, we see the hyperparameters used for this experiment. I used only a small part of the original dataset to perform this quick demo. Skipping the warnings, we can see that the server started and waiting for clients. Then again in the upper left terminal, I am deploying the clients. The container's image is the same, only the entry point script is different based on input arguments. After all clients are up and running, the server sends a global model to them in order to start their local training. As you can see in the bottom terminal, this is the beginning of the first Federated Learning round. Now the clients train their local models and then send back to the server the models. The server aggregates them and starts a new Federated Learning round, and so on. And by the way, the cool thing about pre-recorded demos is that they cannot fail. Cool. Now that we've seen how we can simulate the project in a real environment with Kubernetes, we have only one remaining part of the presentation, namely results. The simplest way to acknowledge the quality of generated images is to simply use your eyes and compare them with samples from the original dataset. From this comparison, we can clearly see that the patterns are very similar, despite the complexity of the problem. But you may say that the image level characteristics are not enough. So let's employ t-SNE. t-SNE is a dimensionality reduction algorithm. Very briefly, each image is passed to a computer vision model, which will extract a numerical vector called embedding. These embeddings can be associated with the inner representation of that image. But due to its high dimensionality, 1024 in this case, it's hard to say if two images have similar properties. For this, t-SNE is used. Having all these embedding vectors, we can feed the t-SNE algorithm with them, and it will learn to map from 1024 dimension vectors to a 2-dimensional space. It learns this mapping, preserving the neighborhood structure of our data. That means things that are close in the embedding space should remain close in the 2D space, and things that are far in the embedding space should remain far away from each other in the 2D space. And here are the results of t-SNE algorithm applied on the original and on the augmented one. The separation between classes is clear, showing that the augmented dataset resembles the original data points. One more interesting metric is fit score. This metric compares the distribution of generated images with the distribution of real images from the human eye perspective. It is used as a common metric to evaluate the quality of generated images generated by a generative model. Smaller fit score means that two image distributions are very similar. As you can see, during training, the quality of images improved, and on the same way, the fit score decreased. And here, we have a comparison between some images generated in the centralized setting and some generated samples in the federated learning context with 2 and 4 hospitals. As you can see, the images are very similar, concluding that in the non-centralized approach, we can generate images of equal or superior quality compared to those from centralized setting. And lastly, if talking about numbers and improvements, we managed to enhance the classification accuracy on the original non-augmented test set with 3% after augmenting the dataset with the presented framework. At first, it may seem that 3% is a small improvement. But if we remember that we are talking about the medical domain, this 3% can make the difference. And with this being said, this is a good moment to end the presentation. Thank you for your attention.
It can change the overview final results. What happens in that case?
Yeah, if you remember, I had a slide with the aggregation server, and there could be multiple aggregation functions, one of them more complicated than another, and you can add logic in the aggregation function to be more complex and tackle these problems.
Does this aggregation phase happen asynchronously?
Sorry, can you repeat?
Does this aggregation phase happen asynchronously, or how the hospitals send it?
Currently, it works in a synchronous way, but I think you can modify the implementation to also work asynchronous.
Thank you.
Hi. So very nice
Be
presentation.
careful with the question, please.
My question is that in implementing this system, you are assuming that each hospital gathers data in the same way. So, for example, if they might use different technologies to capture their pictures, we may expect differences in the data sets that they produce and consequently in the models. So would this tie down your solution to the necessity that they use the same technology?
Yes, for sure, yeah. The data must be standardized, and the same procedures of gathering the data must be the same for all hospitals in order to work. It will maybe dramatically downgrade the performance of model.
Thanks.
Hello.
Hi.
One question related to the images, basically. So
to the data set?
Yes, and what the hospital sends to the cluster.
Okay.
Usually a histology image looks like the examples we've seen, but various hospitals may use different antibodies, and the resulting image may change. It may have different colors depending on what structure it finds and what kind of cell it finds. Does the model discriminate on this?
Yeah, I think this question is related to the previous one. And if there are slightly changes in the data sets between hospitals, I think the model will be able to learn across distributed data sets, and it will learn to generalize better. If the changes would be dramatically, let's say, between two hospitals, this will downgrade the performance of the model.
Okay, so basically the hospitals will be constrained to send only images with certain antibodies, for example,
right?
Okay, thank you for answering.
More questions? If not, thank you so much for your time.
Okay, thank you. much.